So we're beginning Unit 3, which is going to be focused on linear and exponential growth and decay. Most specifically here in Section 8A, we will be looking at an overall view of linear growth and decay, linear and exponential growth and decay. This particular section is designed to be an introduction, so it doesn't present the formulas that you'll get in the subsequent sections. So for that reason, this particular section will do things in a more rudimentary way, so more steps would be involved. But just so you know, if some of you already know about linear growth and decay and you know some formulas to use, by all means feel free to use them, and that once you get into the subsequent sections and you see those formulas and you've got them, and you should get them by then, that you can go back and use them in whenever you're tackling problems like this. But they use this as a kind of an introduction to give you a logical progression into the formulas without just saying, oh, here are the formulas, work with them, that sort of thing. So with that said, I am working through Section 8A's notes. I'm going to have the solutions key here and not going to write everything down. So for example, you can see here linear growth and exponential growth from the solution key. It says that it's a quantity that for linear growth grows by the same absolute amount, which you're going to find will be a fixed value per unit of time, whereas exponential growth is going to be a quantity that's growing by the same relative amount, which you're going to find is going to be a fixed percentage per unit of time. I also put on the solution key a nice throwback to Unit 1 for you, because if you notice here from the definition, linear growth is representing an absolute amount. If you remember in Unit 1, we have what was called absolute change, which was by definition just your new amount minus your old amount. And if you recall, new minus old was just going to give you one fixed value. Whereas an exponential growth is a relative amount. We had back in Unit 1 what was called relative change. And relative change was your new minus your old divided by your old times 100, which was always giving you a percentage. So hopefully you're going to see some parallels and a nice transition from what you did back in Unit 1 to in terms of these problems. These two definitions focus solely on growth, but it should be noted that linear and exponential decay also exists, and we will be talking about it. It just represents a decrease per unit of time by either a fixed value or a fixed percentage. So let's start here with example 1. I'm going to run through this one from top to bottom. In example 1 is talking about Sally, who's gotten a new job, and her employer has given her 2 ways of being paid. Option 1 says she's going to get paid $100 on the first day of the month, and every day of the month after that, they're going to give her $50 more than the previous day. Option 2, on the other hand, she gets started out a whole lot lower, at a penny on the first day, but every day of the month after that, they're going to pay her twice as much as the day before. So we want to figure out then which salary option should Sally take. So let's first, here on this page, just focus on option 1. So if you recall from option 1, it said she got paid $100 on the first day, and then every day after that they were going to pay her $50 more. So that would mean then on day 2 she'd be making $150. Day 3, $50 more, so she'd be making $200. Day 4, $250. Continuing on, I'm not going to take your time here in this video to write out every single number. By day 15 she'd be making $800. Day 16 then obviously $850. I'm going to go on down to day 29. She'd be making $1,500. And lastly, by day 30, they'd be giving her $1,550. So here we're trying to figure out now, option 1 represents what type of growth and why. And that's ultimately here what we're going to try to figure out with these two options. Which one is representing linear, which one is representing exponential growth. So probably the best and easiest way to look at it is look at between any 2 consecutive days, and it doesn't matter whether you choose day 1 and day 2, day 3 and day 4, or if you come down to day 29 and day 30, or day 21 and 22. Between any of those consecutive days, you will see that the change between each of those is a consistent $50. Doesn't matter which that you choose. And so since it's a consistent value there of $50, then that represents linear growth. Okay, so I would say that this represents linear growth because it increases by the same amount, and I'm just going to write by the same amount, which in our case here was $50 per day. So ultimately then that just says, well, the first salary option then is going to end up paying Sally $1,550 by the last day of the month, and her salary for the entire month would be to add up day 1 through day 30. And if you did that, you would find that she'd be making a little over $24,000, $24,750. Okay, not a bad salary. So if we flip it over on the next page and we say, okay, let's look at option 2 so that we can ultimately compare the two. So in option 2, it said that she was going to get paid a penny on the first day, and then every day after that, they were going to pay her twice as much. So that meant then on day 2, if we double that, she's going to get paid 2 cents. And then if we double that, 4 cents, twice as much now, 8 cents, keep going, 16 cents. Likewise, by day 15, she would be making $163.84. Day 16, $327.68 after you doubled that 163. Ultimately, I'm going to come on down to day 29. Day 29, she'd be making $2,684,354 and 56 cents. Double that, and on day 30, they would pay her over $5 million, $5,368,709.12. So, as you can see, you can already tell then, which option she should go with. Option 2 represents now what type of growth and why. Probably the easiest thing to do is knock out that it's not linear, and you can easily do that again by picking any 2 consecutive days. Again, if I pick day 1 or day 2, day 4 and day 5, those are the easiest numbers here to look at. Day 1 and day 2, she's increased by a penny. Day 4 and day 5, she's increased by 8 cents. Already, it's not the same amount. So once it's not the same amount, then we want to say, okay, is it the same percentage? And so that's where the idea of relative change comes into play. See if it's the same percentage. That's your new amount minus your old amount. I'm going to go right here with day 4 and day 5. So my new amount would be day 5. Take that 16 cents minus the old amount, 0.08. I'll divide it by 0.08 and then multiply by 100. If you can do it on your calculator all at one time, be sure to use parentheses up top. And if you do that, you should find that that ends up being 100%. And so it's a 100% increase from the previous day. And so and it would not matter. You can do this from between any 2 consecutive days if you want to prove it to yourself. It would always be a 100% increase. This again is another throwback to Unit 1. If you remember, when a quantity was doubling, it was a 100% increase. When it was tripling, it was a 200% increase. So don't let the word double to you mean, oh, it's increasing by 2, so that's linear. Doubling is increasing from the previous amount, so you can see here what we've just illustrated, that's a 100% increase. So here we can say option 2 then is exponential growth, because it's increasing by the same percentage, 100% each day. Okay, I'm not going to bother writing these numbers down again, but the second salary option then you can see is going to end up paying Sally a little over $5 million by the last day of the month, and then ultimately her entire salary for the entire month will be to add up day 1 through day 30. This is a nice haul, over $10 million. So if you did this, it'd be $10,737,418.23. Okay, so clearly it's a no-brainer here. It's in Sally's best interest to go with option 2 for her salary. Hopefully that gave you a nice difference between exponential growth versus linear growth. A fun fact, and again, a nice throwback to what we talked about in Unit 1. If you recall, back in Unit 1, the U.S. debt was at $17 trillion. In 50, at the rate that Sally's making in this money, in 51 days, she'd be making roughly $22.5 trillion, which would be more than enough to cover the U.S. debt. I'll let you be able to answer the next couple of questions there from the solutions key. A couple of facts down here at the bottom. The first fact is just talking about how, for example, if you notice here, the first two, if you add these two together, that's 3 cents. It's 1 penny less than the next one. If you add the first three here together, that's 6, 7 cents. That's 1 penny less than the next one. If you add these together, you're going to find that's 15 cents, which is 1 penny less. So that's what it's saying, that all the sum of these is approximately what the next doubling would be. And then the other fact that it says down at the bottom, in general, exponential growth cannot continue indefinitely. In most cases, there's impossibilities for that. A good example I can give you is the rabbits. Rabbits get together, they breed, and if there are certain constraints, either food supply is going to run out, space is going to run out, and they're not going to be able to continue to mate and double in a controlled, fixed environment. If you had a particular space that you were confining them to, that exponential growth could not continue indefinitely. They're eventually going to run out of either space or food or something. Okay. I'm going to flip it on over then to your next page, and I'm going to run through the majority of this particular problem just because I want you to see a couple of things, and then let you finish it up with the solution key. There are two towns, Centerville and Mapleton. They both have initial populations of 5,000 people. Centerville experienced major negative changes impacted by the recession, which caused folks to move out of the town at a rate of 200 people per month. Mapleton, on the other hand, experienced a growth at a rate of 10% per month due to a number of positive economic changes. So again, the population represents two different types of growth and decay. We want to fill in the population for the first year for each town. And you might want to pause the video at this point and do Centerville, because Centerville is linear. As you can see, it was 200 people per month, and so it's very straightforward. Mapleton is the reason why I'm doing this part of the problem, because I want to give you a concrete way of making sure that you can get these numbers in this column. So Centerville, it said, okay, that at the start it's going to have 5,000 people, and then it was decreasing by 200 people per month. So 1 month later, then it only had 4,800 people. A month after that, 4,600 people. And then 4,400, and so on until you get to month 12, and that population is going to be down to 2,600 people. Okay. So Mapleton, on the other hand, still started out with a population of 5,000 people. They're experiencing growth at a rate of 10%. That percentage should be your cue that, hey, this is exponential. If you recall from back in Unit 2, you had a formula where you had the original amount plus or minus the percent times the original. And this is one of those cases where you're going to have a better formula for exponential, but this is a nice way to introduce you to exponential in terms of how it builds from what you've already learned before introducing you to this other formula that you'll see later on. So here in the beginning, it has a population of 5,000 people. 1 month later, it's going to experience a 10% increase. So what's going to happen is it's going to have that 5,000, the original population, plus 10% more. So here's what you can think about. It's going to have its original population, plus it's going to experience a 10% increase on that population. Well, that original population then each time is going to be changing, so I'm going to say, well, that's X. And then 10% of that original population. In front of this first X, that's a 1. And so these are coefficients here that can be added together. So 1 plus 0.10 would be 1.10X. And some of you might be thinking, I can figure this out. And by all means, certainly, you know, a different way, and by all means do so. Here is one way, and like I said, it is a throwback to what you've done before. But now what I can do in order to figure out how many people are there 1 month later, I can take 5,000 times 1.10, and that's going to give me 5,500 in one fell swoop. Some of you might say, well, I'm going to take 5,000, multiply it by 10%, 0.10. I'm going to get 500, and then I'm going to take that 500 and add it back to the 5,000. That's essentially exactly what I'm doing right here, is that I'm taking 5,000 and multiplying it times 10%, and then ultimately adding 5,000 back in. So this is a quicker way to do it at this point, 1.10 times x. Now here to get month 2, I'm going to take the 5,500 and multiply it times 1.10. I'm going to always round these to nearest whole numbers, so that would give you a population of 6,050. But again, if you wanted to work through it step by step, it would be 5,500 times 0.10, then add that to 5,500. 3 months later, take that 6,050 and multiply it times 1.10. You'd have a population of 6,655. Take that and multiply it times 1.10, 7,321. Keep on and so on until the end. You're going to have 15,693 people in that town. Right away, you should be seeing, okay, this is decreasing by 200 people every consecutive month, whereas over here I'm increasing by 10% each time, which is the difference between linear versus exponential. I'm not going to go through the graph here. You can see from how I did on the solution key, I put the months down here. To figure out the scale for my y-axis, it was, it had to be the population. You can see that your lowest population was 2,600 and your highest population was a little over 15,000. So that's why I chose to start at 1 and just go by each one. I had enough room. In some cases, just like we talked about in the previous unit, make sure your scale's uniform. If you want to start at 2,000 and then count by twos, by all means, that's perfectly fine. What you should, though, ultimately find is that Mapleton, I'm going to go ahead and put in here 1, 2, 3, 4, 5. They're both going to start at this 5, but you're going to hopefully see that Mapleton is going to be increasing, and you're going to have somewhat of a curvature nature, and I'm just going to label this as Mapleton. I'm being very shorthanded here. You've got great notes listed there, on the solution key. Centerville is going to start also at 5,000, but it's going to be decreasing at a fixed amount, and so you're going to see that it is decreasing in a more linear, straight fashion, and that would be Centerville. So linear is always a straight line. Exponential has that curvature to it. Okay, so we would say here that Centerville then. Well, I'm going to let you work through the last part of that so that you can take a moment to process everything that was being said there. I'm going to flip it over to the last page. I'm going to work through A and B, and then what I would recommend that you do is to pause the video. I'm going to work through this entire page. You probably want to see me work through A and B, and then what I'd recommend that you do is pause the video after we do B, and then work through C, D, and E on your own, and then go back, watch the video, check yourself with the solution key, that sort of thing. But this page is very important. Essentially, it's putting everything together, and these are the type of problems I'd be expecting you to be able to compute through at this point. So here in example 3, you're going to determine whether or not these situations represent growth or decay that's linear or exponential, and then answer the associated question. So here in part A, it says the number of students at Wilson High School has increased by 50 in each of the past 4 years. So my Q here is a fixed amount per unit of time, so that's telling me a fixed amount linear. And because it's increasing, we go with growth. Okay, so now answering the question, if the student population was 750 4 years ago, what is it today? So I would take that 750 and I'm increasing by 50 each of those 4 years. So I'm going to increase by 50. I can say, okay, there's the first year, the second year, here's the third year, and here's the fourth year. We could say, well, that's 750 plus I'm going to increase by 50 4 times. Either way you want to do that, okay? Ultimately, it doesn't matter how you compute that. You should end up with that being 950 students. 4 years later. All right, in Part B, it says the price of milk has been rising 3% per year. The percent, a relative amount here, excuse me, a relative amount would be a exponential, and because it's rising, we would say growth. I'm going to use that formula that you saw just a minute ago. The price of gallon of gallon of milk was $4 a year ago. What is it now? So you saw me write this a minute ago. Original, since it's increasing, I'm going to use a plus sign, percent times original. Because what's happening is you're going to pay the $4 plus you got to pay how much it's increasing by. It's 3% of that $4. And so then you would find that that would be $4.12. Again, if you find $4.12 a different way, all that I care is that you get $4.12. Okay. All right. So again, if you want to pause the video, you can certainly do that at this point. So now looking at Part C, it says tax law allows you to depreciate the value of your equipment at $200 per year. Fixed amount, linear, decay, because I am depreciating. You purchased the equipment 3 years ago for $1,000. What is its value today? So you start out with $1,000, and then you're decreasing it by $200 each year for 3 years. So we can do it like that, like I showed you before, or you can do 1,000, take away $200 for the first year, the second year, and the third year. So taking away $200 each time, doesn't, like I said before, doesn't matter how you do it. Regardless, we should all end up with end value of being $400. I don't need so many dollar signs. All right, so then I'm going to scoot on down to letter D here. It says the memory capacity of a computer storage device is doubling approximately every 2 years. This is the one that's deceiving. Doubling, if you remember back when I was talking about one of the previous problems, doubling represents a 100% increase. So for that reason, we're talking about exponential growth. So in this case, if the company's current device holds 16 terabytes, what will it hold in 6 years? So you start out with 16. And since this, I can use my formula, but since it's doubling it, working through it, I can say, okay, well, at the end of the first year, or the first, let's see, it's doubling every 2 years, so we got to be careful about that. Doubling every 2 years, so in 6 years, it's only going to get to double 3 times. So we double 1 time, and we have 32 terabytes. That would be 2 years. Okay, so now 32, let's double that, and that's going to be 64. That's at the end of 4 years. Take that 64, let's double it, and that's going to be 128. So 128 terabytes would be the end of my 6 years. And again, I only did that 3 times because it's doubling every 2 years. So in 6 years, there'd only be 3 times to actually double. If you wanted to work through the formula with that one, it'd be your original amount plus you are so like I was saying, if you want to use the formula, your original amount would be 16 plus your percentage is 100%. So 100% changed to a decimal would just be 1 times 16. And so 16 times 1 is just 16, plus 16 is going to give you 32. So, but that's only takes into account the first doubling. So then you've got to repeat 32 now, plus 100% is just going to be a 1 plus 32. which is going to give you 64. So that's the reason why I chose to do it this way over here on the left. And then likewise, you can do it one more time. 64 plus 100% would just be 1 plus that 64, which would give you 128. So just so you know, you could use the formula. In letter E, the price of a high-def TV has been fallen 25% per year. By now, it should be very ingrained for you that a percentage represents exponential, and it's falling, so that would be exponential decay in this case. If the price today is $1,000, what can you expect to pay in 2 years? So let's take our original amount, $1,000, pay 25% less, so we're going to do subtracting. Take that 25%, change it to a decimal, 0.25, times the original. That's going to give you a value of $750. That's just the end of the first year. We want 2 years, so now take that amount, take that $750, decrease it by 25% of the $750, and now you would be sitting at paying $562.50 at the end of the 2 years under that particular exponential decay.